Okay, today I'll be talking about ventricular pressure volume loops. These are useful for understanding how pressure and volume change over a cardiac cycle. So in other words, one heartbeat. They're useful for illustrating how the heart responds to changes during exercise and during disease state. Now, pressure volume loops are a little bit unusual for people that simply aren't used to this way of plotting data. So I'm actually going to take you through the very first one in some detail so we make sure we understand how this works. So first of all, they're typically plotted this way with volume on the x-axis, say in milliliters, and then on the y-axis we have pressure in millimeters of mercury. And let's put some numbers to have some reference points here. 50, 100, and 125 milliliters. Let's put 20 millimeters of mercury, 80, 100, and 120. Okay? So the way these are done, you can really start at any point in a cycle. So let's start in a relaxed state. So we're looking at the left ventricle. I should mention that here. So the left ventricle is relaxed. In other words, it's in a state of diastole. And so we'll start at the beginning of diastole. So the pressure is low. It's about 20 millimeters of mercury. And let's say the volume is about 50 milliliters inside the left ventricle. Now at this time, the mitral valve, which is the atrioventricular valve between the left atrium and the left ventricle, is open. And so as actually diastole started here, we'll get back to that in a second. So this is part of diastole though. And so as the left ventricle relaxes, pressure goes down, as you might expect, but it's also filling, and so volume goes up. So it's relaxing, but volume's going up. Eventually you hit a low point, and then the volume continues to increase. So the left ventricle is continuing to be filled, right, as it's going up here, but at the same time, the pressure actually starts to come up again. And that's because at this point, the left ventricle is being passively distended by the blood that's entering the left ventricle from the left atrium, which is in turn being filled by the pulmonary vein. So there's essentially blood pressure coming back and helping to fill the left ventricle. And so we can call this the filling phase. And we could go into more detail. For example, early on, it's the rapid filling phase, and late, there's an atrial kick. But for now, let's just call that the filling phase, and then move on to the next phase. So after diastole, you enter the phase of contraction, right, which is called systole. And so we'll draw that. I'm switching colors here. Now you notice I'm drawing this as a straight line, which seems very odd. Essentially, this means that the volume is not changing at all, whereas pressure is increasing during this early part of systole. And that seems pretty strange, right? Like if we're having active contraction of the left ventricle, you could ask the question, well, why isn't the volume going down? If I had a syringe and I pushed on the plunger of the syringe, wouldn't the volume go down as I increased pressure by pushing on that plunger? Well, it turns out the volume doesn't change, and it's because the left ventricle at this point is closed. It's a closed chamber. So let's think about that for a second. What about the aortic valve? Would that be open or closed at this point? Well, the aortic valve during the beginning of systole, during this phase here, would be closed because the pressure within the aorta, this residual pressure, is actually higher than that of the left ventricle. So in order to prevent blood from going backwards from the aorta into the heart, that valve is closed. It's closed whenever the aortic pressure is higher than the left ventricular pressure. Okay, so the aortic valve is closed. What about the mitral valve between the left atrium and the left ventricle? Well, that one's actually closed also. It's very early during the beginning of systole, during this phase here, the pressure within the left ventricle actually exceeds that of the left atrium. So again, we don't want blood flowing back in the wrong direction. So the valve is designed such that whenever the pressure is higher in the left ventricle compared to the left atrium, then that mitral valve is closed. So we can go ahead and write that in here. Let's call that. Let's say that the mitral valve is closed to help us remember this. Or it closes right around that time. And so for people, so if you think about the heart and the sounds that it makes, that's actually the very beginning of what we typically think of a heartbeat sound, which is the lub sound. And that's due to the mitral valve closing, and also, of course, the atrioventricular on the other side, on the right side of the heart, closing at the same time. That causes the lub sound. And so, there's so that's what's going on there. So now the next thing, of course, is we see, so then the pressure is increasing, but the mitral and aortic valves are closed, and therefore there's no change in volume. And so there's actually a name for this. This is called isovolumetric contraction. Isovolumetric contraction. Okay, and that occurs up to a point, up to the point in which the aortic valve opens. So at one point, so there's, remember, residual pressure in the aorta. Let's say it's 80 millimeters of mercury. Since the left ventricle is contracting very strongly, at some point this pressure in the left ventricle exceeds that of the aorta. So the aortic valve opens. And then this begins the next phase, which is called the ejection phase. So now blood has a way to go. The mitral valve is closed, but the aortic valve is open, and so blood has a place to go. It's going out from the left ventricle into the aorta. So we call this ejection. And so now pressure continues to increase because the left ventricle is continuing to contract. But at the same time, the volume is decreasing because the blood is being ejected. So we get a new trajectory that goes this way. And eventually we get to a peak pressure, which is the peak systolic pressure generated by the left ventricle. The aortic pressure would be very similar at this point. And then this curve starts to go downwards again. Why does it go downward? Well, let's think about that for a second. Well, the left ventricle is contracting, but at some point, the contraction sort of starts to reach an end where it's contracting, but the volume is getting smaller and smaller, so the contraction is less strong. And so towards the end, the pressure actually starts to drop, although blood is still being ejected. Now, at some point, the pressure within the left ventricle actually drops below that of the aorta. You have to think about what the aorta has been doing. The aorta is actually quite elastic. It's distendable. So it's not only is blood flowing down the aorta, but it's not just a pipe. It also is a little bit like a balloon. So it takes up some of this pressure, and so pressure is built up, and that it's sort of a distended aorta, and so that pressure can actually push backwards on the aortic valve and close it, as long as the internal pressure within the aorta is greater than that of the left ventricle. So let's put that in here. So aortic valve closes. Okay? And that's really, together with, we're talking about the left side, but if you think about it, on the right side, around the same time, the other semilunar valve will close. And that is responsible for the dub or dup sound, which is the second part of the heartbeat. So again, there's turbulence caused by the valves closing that causes the sound, okay? Okay, so this just as a quick reminder, so this was all been part of systole, right? The contraction, first the isovolumetric contraction, then the ejection phase. Those are all systole. So after systole, what comes next? Diastole, of course. So we're going to go into diastole. So the heart left ventricle is now started to relax. And I'll draw what that looks like on a pressure volume loop. And interestingly enough, it just makes a simple straight line. So think about that for a second while I take a sip of water. What does that mean? Why is it just simply a straight line? Okay, so it's very similar reasons. This is sort of parallel in a sense to the isovolumetric contraction. On this part of the pressure volume loop, we have isovolumetric relaxation. So I'll write that in, isovolumetric relaxation. So what's happening here? Why is it isovolumetric? So the pressure is certainly going down. You see that here. But the volume doesn't change. Iso means the same, so the same volume. Well, the aortic valve is closed. What about the mitral valve? It's actually still closed. It closed way back here, and it's remained closed throughout all this. And so again, the left ventricle, it's in a situation in which you have a chamber, which is a left ventricle, in which both valves are closed. So now it can start to relax, but the volume doesn't change. The blood has nowhere to go, no blood can come in, none can go out. So the volume, sort of by definition, has to stay the same. And so there we have isovolumetric relaxation, so the volume stays the same. Eventually we get down to the point at around 20 millimeters of mercury, in which the pressure within the atrium is actually greater than that of the left ventricle. And so what's going to happen there with the mitral valve? That's right, the mitral valve will actually open. So let's add that to our diagram. So the mitral valve opens. Okay? Note that when the valves open, they make no sound. Okay, that's not really a sound-producing event. So the mitral valve opens, and just to complete the circle here, we're going to say, well, at this point now, blood can flow from the left atrium into the left ventricle. And so now you'll see the volume start to increase, right? And at the same time, the left ventricle continues to relax. And so that's the reason why the pressure, even though there's not blood flowing in, the pressure continues to decrease for a while. So you reach this low point. Now eventually, the volume continues to go up, but now pressure increases. Now what would be going on there? Well, the left ventricle is actually distendable. So as the blood flows in, it starts to distend the left ventricle, so it increases in volume. But it's also going to have fight back against that a bit. So pressure is going to increase. Okay, so that's the basic. So the basic idea, I went through this, step by step, and I did this for a reason, because these are kind of unusual diagrams. We're used to looking at plotting, say, pressure versus time or volume versus time. We're not used to plots where you plot pressure versus volume. But these sorts of plots are very common. They're very useful. One thing to think about, though, is we went around this in a counterclockwise manner, okay? So when you look at these diagrams, think about time as going around this way. And the other thing to think about is that time isn't really represented here. So what happens is, I won't give you the exact numbers, but this phase is actually quite quick, taking 0.05 seconds. This phase takes about 0.25 seconds, or a quarter of a second. This phase here is 0.15 seconds, a little bit longer than the isovolumetric contraction during the relaxation phase. But these are certainly quite fast. And then here, this is really the longest phase. It takes 0.55 seconds. I'm assuming a heartbeat cycle of 1 second. Again, that gives you a heart rate of 60 beats per second, which is pretty typical. So if you add up the numbers I just gave you, that gives you 1 second. Okay. So let's move on now, so we've talked a bit about how this diagram looks, but what can you actually use it for? So let's move on and do that. Well,